In this fourth video, we're going to start looking at the real-life applications of nuclear science, the most prominent of which is the generation of power by nuclear fission. At the minute, this generates 20% of the UK's current national output. We're going to take a look at the basics of fission and how it works and how this is implemented in a nuclear power station.
Okay, before we can understand how we generate electricity in nuclear power stations, we'll need to get to grips with a few technical terms first. Okay, the first term we need to be familiar with is nuclear fission. Fission is the process by which a heavy, unstable nucleus is split up into two or more smaller nuclei, and in doing so releasing vast amounts of energy. It's important to note, however, that this is very different to radioactive decay, which, as we learnt previously, is a spontaneous process. Fission is artificially induced by bombarding a fissile nucleus with high energy neutrons. Fissile, by the way, is simply a term applied to materials that will undergo fission, for example uranium-235 or plutonium-239. The critical mass is the minimum mass of fissile material that will undergo fission, and we're going to talk more about that on the next slide. And a chain reaction is simply a self-sustaining reaction. So let's have a look at a specific example. So when uranium-235, a fissile isotope of uranium, is hit with a neutron, it splits into two or more daughter nuclei, as we call them, and releases 3 neutrons and a lot of energy. This is shown in this schematic here. So here we have our neutron being fired at our atom of uranium-235. We temporarily form the isotope uranium-236, which is very unstable, which almost instantaneously breaks apart into 2 daughter nuclei. In this case, we've got an atom of krypton being made and an atom of barium being made. We see we release a lot of energy and 3 further neutrons. These neutrons that are released by this fission can go on to cause another, and this is called a chain reaction. However, in order for this to occur, the mass of uranium that we're using in our fuel rods must be greater than the critical mass. Otherwise, the neutrons simply escape and can't go on to cause another fission. So, as we've said, the energy released by nuclear fission is massive. Actually, if you split one uranium-235 atom, it releases 50 million times more energy than combusting one carbon atom from a fossil fuel. This energy, just as you would do so in a conventional power plant, is used to produce steam, which drives a turbine to generate electricity. A few other things to note. In a nuclear reactor, we must use control rods. As 3 neutrons are released, we need to absorb 2 of them. If we don't, all 3 neutrons may go on to cause a fission and the reaction will run away. This is what we would call an uncontrolled reaction, and this is what occurs in fission bombs, otherwise known as A-bombs or atom bombs, when they're detonated, as all the energy is released very quickly, leading to an explosion from the thermal shockwaves generated by the enormous heat produced. Control rods typically used in power stations are made of boron, which is an excellent neutron absorber. So nuclear power is fairly commonplace, with in 2014 11% of global electricity produced from fission power stations, and in the UK it's accounting for around 20% of the total electricity supply. Many people wonder what are the benefits of using nuclear power, so we're going to discuss that very quickly now. Unlike traditional power stations, no fossil fuels are burnt and thus no greenhouse gases are produced. This is good, as climate change is one of the greatest challenges the human race is facing or is going to face. Fossil fuels currently used in most power stations are being exhausted very quickly, with estimates suggesting that oil will be fully gone by 2052, gas by 2060, and assuming we only use coal once they've both run out, it too will be fully depleted by 2088. As we've just discovered, you produce a lot of energy from a very small amount of nuclear fuel. And finally, compared to renewable energy sources such as solar, wind and hydroelectric power, nuclear power is incredibly reliable. They can operate continuously for 90% of the year without requiring fuel rod changes, and while they're running they provide a continuous supply of energy. So despite the advantages we've just discussed, there are a few drawbacks. Uranium too is a finite non-renewable source, and unfortunately only 0.7% of naturally occurring uranium is the fissile isotope uranium-235. In order to make fuel rods that will work in a power station, we need to enrich this uranium to increase the uranium-235 content to between 2 to 3%. This may not sound very much, but enrichment is a chemically demanding process that is not at all environmentally friendly. The nuclear waste from spent fuel rods and reprocessing nuclear fuel is often highly radioactive and thus extremely dangerous, and remains so for long periods of time. Later on in this series, we have a whole video dedicated to the problems with nuclear waste and current research that's trying to tackle it. Finally, in the unlikely event that you do lose control of a nuclear fission, when it goes wrong, it goes very wrong indeed, most famously as it did at the Chernobyl power plant in 1986, which we're going to discuss next. On the 26th of April 1986, several events led to the explosion of reactor number 4 at the Chernobyl power station in Ukraine, formerly the USSR, during which 5% of 192 tons of fission fuel and byproducts was released into the atmosphere. Ignition of 1,200 tons of graphite casing released even more radiation subsequently. This resulted in 2 immediate deaths and loss of 28 lives from acute radiation poisoning, though the exact number of fatalities is unknown as the effects of lower dose radiation are long-term. 116,000 people living within a 30-kilometre radius had to be evacuated, and the surrounding environment will be radioactive for 20,000 years, although a new sarcophagus has now been built around the exposed reactor core to contain the radiation. In the next video, we're going to look at how potentially dangerous radiation is used in solving the clean water crisis, the food industry, and in medicine.